Amy Wu from Queen's University.
So hello, I'm here to talk to you about what's trunk got to do with it. I think you guys already know the answer from Peter's talk, but it's really great because we kind of approached it from different perspectives, and you'll see that we kind of get similar results. So I think it's really exciting. So when you think of walking, and you think of maybe modeling walking with simple models, sorry. So you think of the angle between your legs is symmetric. So between alpha and beta, you don't really think of it being asymmetric. These are generally equal. And whether you are walking with smaller step lengths or faster step lengths, all these you think of these as equal. So in what cases would you think of where you have asymmetrical interleg angles? Well, for example, if you want to place your center mass position somewhere else relative to your base of support. So if you're walking up slopes, maybe you want to shift your center mass a little bit forward so that you don't feel like you're going to fall off backwards. Or you maybe when you're going down slope, you want to shift everything a little bit backwards so you don't feel like you're going to tumble forward. So just sort of natural things you might think of. If you want to shift your pelvis forward, you could also use that to bring your center mass closer to your leading leg. But you could also just keep the angle between your legs symmetric and just shift your your trunk forward, and you could kind of choose something similar. Or you could do a combination if you want to keep your center mass in the same place and shift your pelvis back and lean your trunk forward. So we wanted to know how does these different changes affect the asymmetry between your legs. So we have walking up slope, down slope, forward lean, backwards lean, and then walking normal. And we think that these different conditions will induce changes in symmetry between your interleg angles. So what we did was we defined asymmetry as the difference between the two angles, where if you were just in normal walking, that your asymmetry would be 0. If you're leaning a little bit, if your pelvis is leaning forward, you have a positive asymmetry. If it's leaning backwards, you have a negative asymmetry. And then basically we're trying to find with different combinations of speed, trunk, slope, center pressure. Center pressure, I mean normal walking and walking on your toes. How does all this affect the asymmetry between your legs? So what we did was we ran an experiment where we had subjects walking on a treadmill, and they had this red line, which is the goal, so a line they're trying to meet, and they had visual feedback of their trunk angle, which is this ball. So this ball is oscillating as they're walking, and we asked them to please just try to keep them on average where the goal line is. And we had them walk at different trunk angles for 0 and 30 degrees, and then from some conditions we had negative 15 and positive 30, and we also had self-selected. We had them walk at different speeds, 0.6 meters per second, 1.2 meters per second, 1.6 meters per second. We also had them walk on different slopes, uphill, and keep in mind they're still doing different combinations, so they're walking uphill and leading their trunk forward, for example. And then we had them walk on their toes, which was kind of awkward, I would say. And so here this subject is walking downhill but trying to keep on their toes. They're not walking regularly. So I'm going to first show that the subjects were able to achieve what we asked them to do. So if you look at the commanded angle and the measured angle, if we ask them to lean back at minus 15, they do roughly about that. 0, they're able to maintain at 0. And this is a lumped of all, when they're walking on different slopes and everything, they're still trying to maintain that goal. So they're able to do it across all these different combinations of trials. So 0 angles, 30 degrees, and 50 degrees. So it's not, so here you can kind of see the difference between, we're trying to make them move through different trunk angles to try to figure out what's going on. And, oh yes. So we had them, when they're on flat ground, that's their 0. So we had them stand comfortably at their 0, and then we would raise the treadmill and decrease from there. So low to the ground, yeah, to vertical, yeah. So this is and they're self-selected here. Then for their center of pressure, this is just the magnitude of the excursion. So if they walk normally, they have an excursion in the sagittal in the forward direction. And then if we ask them to walk on their toes, they have less excursion because now they're on their toes, so there's less distance for them to move for their center of pressure. So if we look at the asymmetry, we basically plugged in all this data and tried to figure out what the different contributions were for speed, slope, trunk, and center pressure. So here I'm just going to take out the components and show you what it looks like for these different conditions. So it's not going to be like a multi-dimensional graph or anything. So here you can see for the different speeds, there's a slight increase in asymmetry. So positive is having your pelvis a little more forward. For the slope, you have this greater change, more positive asymmetry. Trunk, you have this decrease. So when you're leaning, when you lean your trunk forward, you have this strong decrease in asymmetry. And then when you're kind of on your toes, you kind of feel like you want to also shift your pelvis forward a little. So just looking at these different trends, it seems like the trunk is compensating for these different changes in in the slope and the center of pressure, and in a little bit in the speed. The trend is not as strong for the speed. So looking at this, so what? What does it matter? What does asymmetry matter? Why do we have this different compensation strategies when we walk on these different things? So we took a closer look to see what the trunk has to do and what's doing while it's walking in these different conditions. So if you look at first at their preferred trunk angle, what do they naturally want to do when they're walking at different speeds? When people walk faster, they have more of a forward trunk lean. When subjects are walking up slopes, they also prefer to lean their trunk more forward. And then when their toes, they also want to do this. So this is the preferred behavior of, through these different conditions, they would like to lean their trunk more forward as they walk, and that's what they prefer. So then what does this mean in terms of all the conditions we had them prescribe them to do? So yeah, in summary, the humans prefer more trunk flexion when walking faster up slopes and on their toes. So what we're going to do is we're going to look at the joint powers. So we're going to take the ankle, knee, and hip and look at the joint powers as a function of gait cycle, so from heel strike to heel strike of the same foot. This is going to be for different speeds, and just for reference, I have the preferred plots down there so you can get a sense of what happens for the preferred. So for normal walking, this is what the power curve looks like at 1.2 meters per second, and for 0 degrees. And then for moving your trunk forward and then a little more forward. So it's kind of similar to what Peter showed. And if you were to take the power and then we look at the positive work rates, so taking the integral and dividing by stride time, we can then look at the work rates as people change their trunk angle. So if you look at trunk angle, this is increasing flexion here and joint work rates. This is what you'll see for 1.2 meters per second. So you see this slight decrease in the ankle, which we saw earlier, and then this increase in the hip. And I also have to point out that I did fit a line here, but you can see this actually goes up a bit, which I think goes back to Peter's point where the ankle work seems to go up. So yeah, we also saw that, but I fit a line, so I kind of blurred it, But it is true that that happens also in this data. So then and then I also plot the preferred trunk angle and then the work rate at the preferred. And so you can see, so these crosses are the standard deviations of the subject's preferred, and they pretty much fall along on the line. So if they walk at a slower speed, you see something similar, but with maybe less of a slope here. And then at faster speeds, you also see similar thing, but with more higher work, and then maybe a greater rate of decrease at the ankle, and maybe a greater rate of increase at the hip. So to summarize this slide, we found that with more trunk flexion, you would do less ankle work and more hip work, as you saw earlier. So if we look at slopes now, how does this change with slopes? This is the same normal data, so 1.2 meters per second on flat ground. And if we were to look up on inclines, we now have similar trends where you also have the decrease in ankle power and this increase in hip. And you see something interesting happening with the knee right now. So we haven't looked at it too closely, but you see more drastic changes at the knee. And then if you look at decline walking, there's actually no trend here. So for decline walking, you get a small increase in your hip work rates, but doesn't seem to be a benefit for your ankle. So something different maybe is going on for the decline case. So here, similar story. Oh, this was positive. Yeah. So negative is not plotted here, but in general, negative followed the similar trends. As this decreases, I think the negative also decreased. But for the knee, the negative work rates, I think were not significant. They kind of were plateaued. But I I don't have it here. So I'm just looking at positive work rates here. So the story is very similar, except on decline, there seems to be something else going on. So it's uphill walking maybe is not quite the same as downhill walking. Well, in many ways it's not, but we can see that here also. So if you look at center of pressure, this again is the normal plot. And if you go on your toes, there's some differences in the power and then the work rates. But again, you sort of see something similar, not as drastic of a change as if you're going up slopes or walking faster. But you see again this decrease in the ankle and then an increase in the toes. Decrease in the ankle work rates and then the increase in the hip as you lean your trunk more forward. So repeating it like a fourth or fifth or sixth time again, there's more hip work done, but there's less ankle in this case also. So different scenarios, and they all have similar trends. So if we just look at the trends, like the slopes as we change the work rates, as we move through different trunk angles, this is just the bar plots of the slopes. So you can compare the slopes for the work rates. And if you compare like at 1.6 meters per second compared to normal, there's a 1.4 times increase in the rate of work rate increase, and then a 3.7 time decrease in that case. If you look at slope, you have something similar, where you have about 5.6 times rate of decrease versus a 1.6 times rate of increase. And then for toes, it's about 3.6 and 1.3. So kind of similar numbers here. So this is looking at the trends and the rate of change as you change your trunk angle. But if you were to just compare the numbers between having a trunk at 0 degrees versus 30 degrees, which is a condition we had across all the trials, you'll see actually the amount of change was kind of, this kind of story was different actually. So you get on average, a 25% decrease in your ankle work rate, but a 70% increase in your hip work rate. And at first I thought, like, I don't know what's going on here. But there's maybe a couple of reasons. So yeah, there's like a large, maybe a hip sacrifice, seemingly, from like you put a lot in your hip and then you get a little gain in your ankle. And this could also tie back to what Peter was mentioning earlier about perhaps it's more efficient to use push off from your ankle than using your hip to compensate for the collisional cost. That could be some answers. I think there might be more answers, but this is something kind of interesting that could be up for discussion. Another thing was that if you look at decline slopes, for this trial, we also were able to do a trunk extension. So this is showing increasing trunk flexion. If you were to now lean back, we kind of expected that maybe because of the preferred, that leaning back would be helpful when you're walking on declines, because you don't want to lean too far forward. You're going to kind of tumble off the treadmill. But actually what you see is there's an increase in both ankle and hip. So what you found before with walking up slopes or flat ground with your trunk doesn't seem to hold if you were to lean more backwards. So maybe here people prefer to have less of a forward lean, but they don't really want to lean backwards. I don't know, maybe at more extreme conditions they may want to lean backwards, but in this case it seems for the ankle and the hip both actually increase, and there doesn't seem to be any sort of compensatory behavior. So this ankle-hip trade-off might explain some trunk preferences. For example, between healthy controls and subjects with a spinal cord injury, if they were both walking up slopes, subjects with a spinal cord injury would tend to lean their trunk forward more, so it could be used as compensation. Also, between young adults and older adults, as they walk faster and faster, at fast speeds, older adults tend to have 1.3 times more forward lean. So maybe this also, again, using some sort of compensatory strategies between the ankle and the hip. So in summary, what's the trunk got to do with it? So it seems to be countering changes in asymmetry of the interleg angles. So as you're changing your asymmetry, the symmetry between your legs, walking up slopes and these different conditions, you're using a trunk to sort of compensate for that. Also, it reduces ankle work at the expense of hip work. And it does this whether you're walking at faster speeds, up hills, or on your toes. And then just a quick plug, I'm starting a new lab at Queen's University. So if you like humans and like robots and you like Canada, I'm looking for PhD students. So feel free to email me or come talk to me. Thank you.
question?
I have a general question. When you're leaning forward, you have basically no choice but to do hip work, right? Is that true or not? Or do people bounce in a way that somehow they don't do positive work?
Well, I guess here we saw that they always had an increase, but maybe if we could change something else about their gait, we could negate it.
But maybe the task, if you tell them just to hold the posture,
Right.
unless they give more or less constant torque, then they have no choice but to do hip work, right?
Right.
So it's not a matter of them choosing to do it. They're stuck with it.
True, but then they don't, yeah, it's true, but then I guess it plays into their preferred choice. So they could also choose to remain more upright in their preferred walking. So, and yes, and when we prescribe these conditions, they have to do more hip work, but in terms of the preferred case, they don't necessarily have to lean their trunk forward more when they go up slopes, for example.
No, but when you go up slopes, you lose if you don't lean forward, you don't have a collision loss. So you don't have to use the trick of push-off, so you can use your big back core muscles to propel walking. So it seems natural to do, since it's a work performing task, use muscles that do work well. I mean, I don't know, it seems like an optimization would give that answer, wouldn't it? Am I making sense? Do you understand what I'm saying?
Say the last part again.
When the great thing about push-off is that it decreases the dissipation in heel strike.
Right.
Otherwise, if you just want to put work in, you should put it in with the biggest muscles you've got around that put in useful work. And so once you're walking uphill and you don't have much of a collision problem anymore, why not use your core muscles to do work? It seems like an optimization model that would avoid having muscles at high stresses would naturally give that answer, I would think, but I don't.
Yeah.
I disagree. I disagree with one point, which is why do you care if the muscles are big? Like if you're not at the maximum of what the muscles need to do, then
Okay.
from a metabolic cost argument, it shouldn't matter.
From a metabolic cost argument, it shouldn't matter, but everybody who does, works with redundant muscles finds that when you have two muscles that can do a task, you generally use them both, and you don't randomly distribute it in between them. So there is something about there is some cost that prefers lower stress. That's what I understand from everybody who does it, solves distribution problems. Right? It might not be metabolic work, but if you have big muscles, right? If you have two muscles in parallel, you don't just use one of them, you use them both.
Even without considering muscles, an optimization model that has a trunk will find an optimum with a forward-leaning trunk for going uphill.
Right, yeah, and even at faster speeds, as someone showed that when you're walking faster speeds, his neuromuscular model also showed that you would lean your trunk going more.
Yeah, so I think I can also add something to that. So if at least for our the Song and Geyer neuromuscular model, if we optimize for metabolic energy, even for normal speed, the model tends to lean a little bit more forward than like what we observe from humans. And yeah, so it seems like this is extension from like what Peter showed, but in the model it seems like that's a more energetically optimal solution, even when we have muscle models. And one thing I want to add is that when you measure metabolics from human experiments, I think there might be a chance that these human subjects didn't really optimize their gait yet to that new condition. So maybe if you train more with them, maybe they have a chance to have even lower optimization, but just no evidence, but maybe that could happen.
Sorry, just following up on the same question. It seems like when you need to do sort of net propulsion or go up a hill, that a shear force is what you would like, and using proximal muscles to sweep the leg back is going to be I think more effective at producing a shear force just from the mechanics of the interaction with the ground. Then you don't necessarily want a force that's in line with the leg so much as you want a retracting torque at the hip to give you a shear force pushing you forward. So it might make sense just from basic mechanics if you want a shear force to overcome gravity or speed up to do that.
Yeah, and we have ground reaction forces, but I didn't look at that yet, so I think that was something to look at to see if there
people are shaking their heads, but I've seen this really clearly in dogs going uphill, and I realize I'm not by that.
So wondering, so if you put a heavy backpack on somebody, it will presumably pitch their body forward to keep their sort of spine center of mass upright. So in that case, you have a person who's anatomically leaning forward, but mechanically still
Right.
upright. How much of this would change in that? Like, so like, is how much of the story is just about like where your center of mass is, and how much of it is about where your actual anatomical?
Yeah, that's a good point because we could assume that when you lean forward and then also put your pelvis back, you're actually keeping your center of mass relatively in the same location. We didn't look at that, but I think that would help explain also is that prefer to keep it there. So if you're wearing a backpack, do you actually both lean forward more and then shift your pelvis, or do you, keep your center of mass at the same place and then do other shifting?
I'm not sure if you mentioned this, but I know Peter mentioned things like, well, you get to like your hamstrings are lengthened out and stuff like that. So if you pitch your body forward, you're doing things to your muscles. Even if your mechanics still look like your center of mass still looks like you're upright.
Does it look like I'm upright?
Well, if you have a heavy backpack on, so you lean forward, so your center of mass, in that stick figure is still, where it was without the backpack, but you stretched your hamstrings and all that kind of stuff. So
Yes, yeah. So I think comfort could be some part of it. Like if you wanted to lean your pelvis forward and then keep your trunk upright, like there's a bit of maybe like it's not very comfortable for you to. It's more extension in that case, and you have more leeway going forward than backwards. So I think some of it from the hamstring or from just like feeling it in your hip could be related to it, but I didn't really capture it here.
So in follow-up to that, I find myself wondering if anybody ever climbs up mountains, who is climbing up a mountain, switches their backpack from the back to the front, so that their torso is upright but the load is out front. Is that a thing? Okay. So it's an interesting question. So if we can do one that doesn't hinder the breathing,
Right, that'd be really
what would
interesting.
happen to keep the anatomical posture the same while moving the center of mass?
Right.
I think you do move your backpack up and down when you go up and down hills.
Higher and lower.
Yeah.
Sherpas pile it high.
Yeah, exactly. When you go up and when you go down, you do.
It's a,
chest pack carrying a baby uphill is easier.
Yeah, I think
the baby attached to the front of you does not help walking. At least right now.
I think Sam and I were playing with different configurations of trying to have like a heavy load in the front if we could bias him forward or backwards, but fun experiments I think we could do to tease it out.
Allison, move the baby up.
I'll work on that.
Okay, let's thank the speaker.